And here we go. So we're in a good place. So here's what we did on Tuesday. So last class, we stated and worked with properties of the integral. So I'll just write it in its beautiful form. And then what we did is we attempted to motivate what's called the fundamental theorem of calculus. So this is going to be something you're going to want to know what it is. And how did we try to study that, or to try to motivate it, I should say. We tried to motivate it by studying what we called area functions. So we'll remind you what we did in a second. So I'd like you to pay attention to the language I'm using. You notice I said we attempted to motivate. You know, I'm not going to pretend that when I come here and babble for an hour that it makes immediate sense, because it doesn't. I am trying to motivate some ideas, and it's up to you, the learner, to take what I give and then take your other resources and try to go and figure out what all this stuff means. It is not easy to do. And so we're trying our best to get you to understand this. That the process of learning is not necessarily done here on Zoom or usually in a classroom. That is a supplement to the learning. But learning is really, it's up to you, the learner. The best we can do is assist and supplement and answer questions you may have. But most of the stuff, the discovery, comes from your end. So with that in mind, let's recall what an area function was. So what is an area function? So these guys are this type of function. So the variable is actually the upper bound of the integral. So let's make sure you understand that. That is the guy that moves. That's the variable that adjusts. So what do we call t? So this is going to be new to some of you, although it's not typically new because you've done it before. So we call t the variable of integration. So we tried to point this out before, and we'll continue to try to remind you of this. But what does it mean to be the variable of integration? This is what we usually call a dummy variable. As it is arbitrary. So what do I mean by that? Well, let me try to emphasize what I mean on the next page. So when you were in algebra class, or you might have studied things like, just like 3x squared plus 4x equals 0, and 3t squared plus 4t equals 0, and 3y squared plus 4y equals 0, etc., are the same equation. We're just using a different variable. If I now write an integral AB f of x dx, AB f of y dy, AB f of t dt, heck, even like integral from a to b of f of star d star, etc., are the same integral. So the letter is immaterial provided the context says it is. Does anybody have a question about this? Okay, so what did we sort of discover? We did a few examples last class with these area functions, and we had a conjecture. We had some pattern we saw. So through examples, we saw a pattern with these types of functions. And so what was the pattern we saw? We saw this. We saw that if a of x had some form, which I'll write like this, then its derivative was just the function that we meant to integrate. So we did 3 examples. We did the function f of x constant, we did the function f of x equals x, and then we did the function f of x equals x squared. And in all 3 cases, we saw this pattern. And so the question that we then ask ourselves, does this pattern always hold? So that's the first question we might ask ourselves. And then the second question we might ask ourselves is, if so, is the relationship useful? So does the relationship exist for every function? And when it does exist, is it just something cool that happens, or does it have practical use? Any comments, questions? Okay, great. So here's some exciting news. In many cases, it is true. And not only is it true, and it's also very useful. So let's see why it could be useful. Does anybody have any questions before we do this? Okay. So let's investigate how it can be useful. So assume that a of x satisfies the definition above. So that is, we know that a of x equals the integral from little a to capital X of f of t dt. And thus, this relationship is also true. Okay, so what we want to do now is we want to do some deductive reasoning. So we have a area function. We know that if we differentiate this function, we just get the function whose sort of area we were investigating. So let's do some deductive reasoning. What we want to do now is suppose there's some other function out there. So we want to suppose that there's another function, g prime, that satisfies its derivative is also f. So now we have two functions out there whose derivative is both f. Now, the first thing you might say is, well, how do I know that that guy's there? Well, there's a couple ways you can think about this. The first way you can think about it is if f is continuous, then he's always there, because we can always compute the area under the curve by this area function. And then you might say, well, then G has to just be that A. But that's not necessarily true, because as you guys know, if I differentiate a constant, its derivative is 0. Which means what? Well, it means that G and A have to have this relationship. This means that G of X must be A of X plus a constant. I mean, look at that. If you don't believe me, just look at this last line I've written. Differentiate the left-hand side and differentiate the right-hand side, and you get f of x. Again, take this last line that I've written and differentiate both sides. If you differentiate both sides, you get g prime of x equals a prime of x. And so through deductive reasoning, we realize that if G and A both have this property, then they must be differing by only a constant. Okay, now let's compute some values. So I'm going to take G of B and I'm going to subtract G of A from it. So what is G of B minus G of A? Well, we just said what this is. This is A of B plus some constant, and then it's minus A of A, of lowercase a, plus some constant. Now, if we distribute that minus sign, this becomes A of B plus C minus A of A minus C. So right away, what happens? Right away, these C's add up to 0. And what I'd like to do now is write these things in terms of integrals. So what this is this is the integral from A to B of f of t dt, or f of x dx, it doesn't matter. And then this is minus the integral from A to A of f of t dt. But as we stated last class, this right integral must be 0. That's how we defined it. This is just equal to 0. And so what we have now is we have a beautiful relationship. We have that the integral is nothing more than the difference of two numbers. So take your time machine and let's go back to the beginning of our discussion on Tuesday. If we go in that time machine, what we'll remember is we said we'd like to find an efficient way for computing integrals. And in order to find that, what we did is we took special examples. We took an integral of a constant, then we took an integral of a line, and then we took the integral of a parabola, and we studied their area functions. Or we studied the area under those curves as functions. And we recognized the pattern. That's what we did at the end of class on Tuesday. Once we recognized that pattern, we said, well, maybe this pattern's useful. And so if we believe that it agrees, if we believe that when it's true, it's useful, we ask ourselves, what is its use? So now I did this calculation, in which you're going to say, well, I would have never thought of that. Well, no crap. That's why we're doing it. That's why it's in books. It's not easy. It took human beings a long time to figure this out. But now we're showing you that it's true. So what did we just verify deductively, or what did we just reason? What's the moral? The moral is what follows, or the moral's what follows. The moral. The integral of f of x dx can be reduced to the difference in g of b minus g of a, where g of x is any function g can be any function that has the very simple property. Any times g primes equals f, this will work. So since this type of g is very, very useful, we're going to give it a name. Any g with this property is called an antiderivative. Hopefully you see why, because the derivative with the prefix anti in English, that means opposite. Does anybody have a question or a concern? Don't forget, and we're going to do some examples shortly, so it's all this generic letters are going to be replaced by specific functions and numbers. Comments, questions? Okay, so before we summarize all this and state it officially, let's look at, does this check with our previous knowledge? So let's see how this checks with what we know, or what we computed the last few classes. So suppose we wanted to compute 0 to 1 of x squared dx. Now, we computed this a handful of times. We found it to be 1/3. Now, let's apply this to the previous thing. Well, note g of x, which is 1/3 x cubed, is an antiderivative. It's an antiderivative specifically of x squared. Take the derivative of g, you get x squared. So that means it's an antiderivative. Thus, this integral would be g of 1 minus g of 0, which is 1/3. And that is precisely the number we got each time we computed this in the past. Does anybody have a question or a comment? Okay, so let's look at another example. So on Tuesday, we used some properties to figure this creature out. So this guy would be g of 3 minus g of 1, which is 1/3 times 3 cubed minus 1/3 times 1 cubed, which is 27/3, which is 1/3, which simplifies to 26/3, like we computed last class. Does anybody have a question? Comment? Do you hear the kids' music upstairs? They're learning their numbers and letters. Does anybody have a question about this?
No.
Okay, so before we go further, it's important that you understand that this is a shortcut. I can't emphasize enough that the definition of the integral is that limit of a Riemann sum. That is the definition. It is a complicated limit. And what we are trying to sort of foreshadow for you or get you to understand is that there's this big, powerful theorem called the fundamental theorem of calculus. And what this theorem does is it oftentimes, not all the time, but oftentimes takes a complicated mathematical operation, the integral, and reduces it to arithmetic. And not just any old arithmetic, but like plug two numbers in and subtract. That's really simple. Now, of course, if you're thinking about this, the obvious question would be, at least it should be, is, well, O'Grady, this only works if I know what G is. So if you look at these examples we just did, you might say, how did you get G to be 1/3 x cubed? Well, there's a couple ways I can illustrate that, but if you just think out loud about reversing the process of the derivative, it's not hard to see the pattern. And we're going to put more emphasis on these patterns in a second, but if you think about the examples, I'm stuttering. I shouldn't mock that either. That was me. But I am stuttering. So if you look at the examples we did on Tuesday we talked about recognizing a pattern. And what you're seeing here is another way of thinking about that pattern. When you differentiate, say, a polynomial, what do? You multiply by the power, and then you subtract 1 from the power. So if I want to reverse that process, instead of subtracting 1, I would add 1. And then instead of multiplying by that number, I would divide. And we're going to point out that pattern more. But if you think about what's on the screen right now, you might say, okay, I add 1 to 2, and then I divide. So instead of x squared, if I want to reverse the derivative or the process of taking a derivative, instead of getting 2x, I go the other way. I get x to the third over 3. Okay, so we need to state this now and see how we can use it as a tool. So this is the fundamental theorem of calculus. Now, to save space forevermore, I will refer to it as the FTC. So there's actually 2 parts to it. Part 1, which we did not prove, but we gave a sketch of the proof. Maybe that can be someone's project for extra credit, the proof. So part 1. If f is continuous on some interval, which I'll denote as a comma b, then this area function is defined for x it satisfies a prime of x equals f of x. So that's the first part. That was, we sort of gave examples to show this was true on Tuesday. And I mentioned to you earlier, it is true in certain senses. One of the times it's always true is if f is continuous. If f is continuous, this is true. Now, how could you prove this? We just gave examples, but you could prove it. You can write out the definition of the derivative and play around with limit properties, and you could prove that. So I'm not going to do it because of time. We've done it, but we want to do more examples because that's what we want to do. But it's something perhaps I'll give as an extra credit assignment. Show, but you asked, maybe we'll do that. So that's the first part. Now, the second part is, so what this part really tells you is it tells you that the derivative and the integral are inverse procedures. They're inverse operations. And what's the consequence of this? Well, this is the one that we're going to use a ton more and more this semester, and for those of you who go to Calc 2 and any other math courses, you will use this. What does the second part say? Well, the second part says if f is continuous and g is any antiderivative of f, then the integral of f between 2 values a and b can be reduced to this arithmetic option. anybody have a comment, question? Lydia clearly does. She's upstairs yapping about something. Okay, so here's the caution. Part 2 is only useful if we know how to compute the antiderivative. Does anybody have a question about this? So this is an important remark. You know, you can't use this formula unless you know how to find G or to compute it. So this means you need to have some sort of catalog of antiderivatives. And luckily, many of them are very easy because all you have to do is think of your derivative formulas. Hi, Ricky. What's happening? Oh, look, Ricky brought us something. You want to show everybody what you brought?
Yeah.
You want to show everybody? Say, look, she brought everybody a beer. That's good, Ricky. Ricky has a beer. Can you go give that back in the refrigerator?
No.
Can you say hi?
No.
Yeah, we don't drink beer in the afternoon, though.
I bet.
Yeah, it's a beer. You can't drink that. Not for 20 more. 20.
No.
Hey, Ricky, show your cast.
No.
Say, everybody, here's my cast.
No.
All right, you got to go upstairs.
No. Okay.
Okay, go upstairs. Take your beer. Take your beer. Take your beer, Ricky. She just said hi and gave everybody a beer.
She wanted you to have it.
I know,
No,
but we don't
not
drink
right
beer.
now.
Not till tonight.
No, here. Come on.
Ames, do you want to say hi to everybody?
Ah.
Ah!
Okay. It's for Daddy.
Okay, Daddy will drink it later.
Daddy will drink it. Yeah.
Show everyone your cast.
Bye.
Say, I'm getting my cast off tomorrow, hopefully.
Soon, yeah. Boo boo. Okay.
All right, Lydia, do you want to come say hi too while we're wasting it? No, they're not. They're all sleeping. I don't even know if they're even on here.
Lydia, go say hi and then give her the.
Oh yeah, the
to
beat.
bring it back up.
Can you take that beer and put it in the refrigerator? Come say hi. Come say hi. They can't see you. Say hi.
Hi.
Okay.
I'm not very nice, so I want to get out
Here,
of here.
go put that in the refrigerator, please.
Why?
Because you don't drink beer in the afternoon. Not on Thursdays, at least. Not during calculus. All right, that was fun. See, that would never have happened in the classroom. All 10 of you here. Okay, so what does this mean for us? This means we need to understand how to compute antiderivatives. So we solved one problem, but by solving that problem, we introduced a new problem. So that's what we have to do now. So what we need to know is, just like so far this semester we needed to know how to take a derivative, now we want to know how to take an antiderivative, or to determine an antiderivative. So there's some good news to this. Some are very easy, just like derivatives. What's the bad news? Many are not as quote unquote easy. So in fact, a portion of Calculus 2 is spent trying to learn different techniques for this. Okay, so let's look at some basic rules, and it's going to turn out to be useful for us to adopt some new notation. Does anybody have any question or comment? Is anybody even here? Is everybody sleeping? Probably sleeping.
So how often do you find an equation with an antiderivative?
Let's say that again. How often?
Yeah.
Oh, I mean, what do you mean how often? You're going to have to do it a lot. Some of them are very easy. So,
Like, is it common in various equation to find an antiderivative or no?
well, okay, so let me answer your question this way. I think you said, is it common to have to find an antiderivative? And the answer to that is very common. Now, fortunately, we have technology that can assist us with that. But in science and engineering, especially, computing antiderivatives is extremely, extremely important because that is the technique for integrating.
Okay.
What we're telling you is if you want an efficient way of integrating, you need to know antiderivatives. That's what we're telling you.
So basically, antiderivative derivative, it's integration, right?
Okay, so not specific. You could say that, but that's an abuse of words. It's similar. Now, what we're going to say now might make that more clear. Your statement. Your statement is not 100% precise, but it's close. So maybe that's a good transition. It's like we're working together here. So let's introduce it this way. So it's useful to adopt a new notation. Analogous to, so let's look at some notation we have. So we have some notation that says something like x to the fifth. What is x to the fifth derivative? You guys will tell me right away it's 5x to the fourth. And if I said, what's the derivative of sine? You would rat off cosine. So this is standard notation for derivatives. Let's do one more example with, say, the chain rule for the fun of it. Suppose we wanted the square root of, how about 3x squared plus 5? Well, this derivative using the chain rule would be 1 over 2 times. So that would be the derivative of this. So what we'd like to do is adopt new notation. So since there's a connection, as we just pointed out, Shobit, and you're on to it, since there's a connection between integration and antiderivatives, it makes complete sense to somehow let the people know there's a connection. So the standard convention is to do the following. So we're going to define what's called the indefinite integral. So here's what we're going to say. We write integral sine f of x dx. Uh-oh, got chaos up. So we write that this equals g of x plus c if g of x is any antiderivative of f. So do not get confused. Notice this integral does not have any bounds because it's a different type of integral. It's called an indefinite integral. So note.
So how do you find the constant?
You don't find it. It can be anything. So again, this goes back to using some deductive reasoning. Anytime you differentiate a constant, what is it? It's zero.
Zero, yeah.
Does it matter what constant is there? Nope. Doesn't matter because when you differentiate it, it's zero. So you could put 23 there. I can put -6. Someone else can put 100. It doesn't matter. It's still a true statement. So note, the first thing is C is any constant. Doesn't matter. We call it an arbitrary constant. Because it's completely arbitrary. Also, and this is most important for you to recognize, there's no bounds. Do you see an A or a B there?
No.
No. So an indefinite integral is actually not a number. So let's make sure you understand this. So we're going to write this down again because it has to be very, 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 very clear to you or you're going to mess it all up. And we don't want you to mess it all up. We want you to learn. We want you to learn. So if I go to the next page, we have the definite integral. Which is this, it has bounds. It is a number. The indefinite integral which looks like this. The only difference in the symbols is that there are no numbers for the bounds. And this guy is a family of functions. So that might seem silly right now, but we're going to do some examples in a second. So I'll put family in quotations because it might not make sense to you, but that's what it is because it's a expression plus c. And since every one of us on the planet can pick any c we want, we have an infinite family. Another way of thinking about this is if you have one antiderivative, you actually have infinitely many. Okay, so let's write some things. We actually know a lot of antiderivatives already. So let's write down the antiderivatives we know. And if you're not sure exactly why we know them, just think about what you know about derivatives. So in this sense, Shobit, since you asked, you can say that antiderivatives and indefinite integrals are like the same thing.
Okay.
Yeah. So let's look at some common indefinite integrals. So let's just go back. So what I want to do here is let's write our differentiation formula. We know that x to the n, if we differentiate it, is this pattern. Now let's write it in terms of integral language. In the integration language, the reverse is, instead of multiplying by n and subtracting 1, we reverse it. So as I said before, what is the opposite of subtracting 1? We add 1. And then what is the opposite of multiplying by n? It's dividing. So the formula to reverse, or the indefinite integral, or the antiderivative, is given by this form. Now, of course, this doesn't make any sense at all if n is -1. So let's remind ourselves here, n cannot be -1 because that formula wouldn't make sense. But we do have, it does make sense if we remember the following. So what's another formula we have? We have the derivative of the natural log is 1 over x. And so that means if we write it in terms of the indefinite integral, the integral of 1 over x is the natural log. Now, of course, the natural log doesn't make sense if it's negative, so we'll put absolute values here so that it makes sense. And it might not be clear to you right now why you would do that, but it is true. Get a different color. You know that, for example, the derivative of, say, cosine. Excuse me, let me write it this way. Let's do sine. So we know that the derivative of sine is the cosine. So if we write that in terms of the indefinite integral language, we know, oh, what did I write? Oh my God, my kids come down and they ruined me. All I hear is the ABC songs upstairs. Does anybody else hear this? This is like we're learning multiple things. You guys should be so fortunate. So this means that the antiderivative of cosine, or the indefinite integral, is the sine. And I put this plus c after it. Does anybody have a question about these three? We'll list a couple more on the next page. So we know, for example, that the derivative of the inverse tangent is 1 over 1 plus x squared. And so we can write that in terms of integrals, and we just reverse it. Does anybody have a question about this? Let me clean this up, actually. This is kind of ugly. Comments, concerns?
So I just had a question. So before we did the integration thing, right?
Yeah.
So I always thought that, let's say if we have one equation and you find the derivative of it, right? And then if you find the integration, we'll get the same equation. Equation we found the derivative of.
Well, let's be careful. We're going to do some examples in a second, and I think that's going to clarify, because what you're saying is partially correct, but you know, it's not that what your idea is correct, but the way you're phrasing it is incorrect. So I maybe once we do some examples, it'll make a little more sense. Let's do one more of these examples. We know that, for example, the derivative of e to the ax is equal to ae to the ax. So if we want to write that in terms of integration language, we would write it as e to the ax is integral. What's the opposite? It would be 1 over a, e to the ax plus c. And here, just to be clear, a is anything that's non-zero. As long as a is non-zero, this is correct. Okay, so let's do some examples now, because I think when we do some examples, this will help, I hope, at least clarify what you were saying. Shobit, I don't know for sure, but I hope it will. As I always do, I want to caution you guys and gals, don't just worry about doing procedures. I mean, again, we have technology that does all this stuff for us. And so what's more important is that you understand what's happening, not that you're just repeating a procedure over and over again. There's a bigger picture here than just computing integrals or computing derivatives. So here's what we can do. Let's do some examples. And hopefully this will clarify. Well, let's sort of set the stage. So those one. So what we can do is we can compute some basic definite integrals now. Now, here's one of the things that we adopt. Again, we love tech, we love these conventions, and it's going to scare some of you, but it is what it is. So it's useful to use a new shorthand. It's useful to instead of us writing g of b minus g of a, it's useful to write g of x with a vertical bar and then put a and b here. It just makes us writing these solutions a lot smoother. And hopefully this makes sense when we do it right now. Okay, so let's look at some examples. So let's start with a relatively straightforward one. So let's integrate 1 to 5 of 4x cubed. I guess I should be more consistent. You have to write dx here. So we'll call this example 1. Okay, so how do we integrate it? We need an antiderivative. So we have to think about, okay, we know the antiderivative. This is a polynomial. It's 4x cubed. So the antiderivative is what? Well, the first thing you could do, there's a couple ways you could think about this, but the way I would tell you to first do it is just reverse the process of the derivative. So this becomes 4 times x to the 4th over 4. And we read this as evaluated from 1 to 5. And of course, what's going to happen here, these 4s just, they're a common factor, so they cancel. And this becomes x to the 4th evaluated from 1 to 5, which is 5 to the 4th power minus 1 to the 4th power, which simplifies to what? Well, 5 to the 4th is 25 squared. And then 1 to the 4th is 1. So 25 squared is what? 625 or something like that? 625 minus 1, which is 624. Does anybody have a question about this?
So the antiderivative is 624, right?
Wait, what's that?
That was the antiderivative we're finding, right? No, wait.
The antiderivative is x to the fourth over 4.
Okay.
And remember, that constant, just like with derivatives, I mean, if the antiderivative, just think about it. Everything we know about derivatives now applies to the indefinite integral or the antiderivative. So that 4, look, maybe this next example will help clarify sort of the pattern here. So if let's take another one. Let's do, say, 0 to 1 of, that's a 0. So let's do something a little different. Let's say 2x cubed minus 4x plus 6 dx. So what we know is this integrand has 3 terms in it. 3, 1, 2, 3. And what we know about the antiderivative is since it's the reverse of the derivative, then all the properties of the derivative apply, which means that's a long way of saying that we can do each piece separately. So this becomes what? This becomes 2x to the fourth over 4 minus 4x squared over 2 plus 6x, and this is being evaluated from 0 to 1. Now, if you're still unsure about how I got that second part of the equation, just differentiate it, and you will agree with me that the derivative of what's on the right-hand side is equal to the integrand. Okay, now, what we do is we first plug in 1. So when I plug in 1, I get 2/4 minus 4 over 2 plus 6. And then I have to subtract what happens when I plug in 0, which is 0 minus 0 plus 0. So you might say, why did you write that? But I want you to understand the procedure that's happening there. So hopefully you will, hopefully you take some time to understand why I wrote it the way I did. And then all you have to do is add up what remains. That's 1/2 minus 2 plus 6. So that's 1/2 plus 4, which is, another way of writing that is 9/2.
So when you say 9/2, right? So that's not the antiderivative, right? That's another
Oh,
solution.
that is the definite. Look again. So it's really about the terminology. I am computing definite integrals, but the process in which I'm using to compute the definite integral requires that I know the antiderivative. So the antiderivative in the second example is just right here. This thing, I don't know if can you see my pen circling around this thing? Yeah, that's the antiderivative. And then the next step, I plug in the bounds. I plug in 1, and then I plug in 0, then I subtract. In the first example, the antiderivative is what I'm circling here, the 4x to the fourth over 4. Does that make sense?
Yeah. So meaning where you said indefinite, where there are no bounds, right? So there we won't be computing it at the end, right? We'll just leave it at the start where you circle.
So, right. And what I'm going to do is, okay, so suppose I pose this question slightly differently. So, and you're going to get this on your homework too. If instead, if all I wrote, let's say the third example, let's suppose I want you to integrate this. Now, what you'll notice here is, do you see any bounds here? There are no bounds here. So by context, this means that what I should get for my answer should not be a number. It should just be the antiderivative plus a constant. So let's differentiate this. This becomes 5x to the 9th over 9. And then the next one, if we're integrating, what's 3/2 plus 1? Well, 3/2 plus 1 is 5/2. So this becomes 2 times, well, dividing by 5/2 is the same as multiplying by 2/5. So this would be, and I guess you could clean this up. Some of us would probably write it as 5/9 x to the 9th minus 4/5 x to the 5/2 plus the natural log of x plus c.
So how do you find the natural log?
How do I find it?
Yeah.
Well, you just know the fact. What's the derivative of the natural log? Ask yourself, what's the derivative of natural log? It's 1 over x. So if you go back a couple pages, we said this is a common one. You know the derivative of the log. In fact, if you really wanted to,
Yeah.
you could be even more specific. You could show that the derivative of the natural log, the derivative of the natural log of the absolute value of x is 1 over x. And so that's how we know that the integral of 1 over x is log. So I'm using my previously known facts to get this. I have to know all these facts for this to work. Again, there's a learning curve to this. Okay, so for the last one, let's do one more example, then we'll go, and then we'll give you plenty of practice with this, and then you can ask questions next time we get together. Let's change letters for the fun of it. Let's say the integral from 1/16 to 1/4 of square root of w minus 1 all over w, dw. So now we're switching letters. Now, this particular one, it's not at all obvious what the antiderivative is. So what you see is, oh, I got to do some work. So one of the things that I'm going to do is I'm going to do some algebra. And I'm going to recognize that I can rewrite this as the square root of w over w minus 1 over w dw. And then this becomes the square root of w over w is the same thing as w to the negative 1/2, and this is 1 over w. So now I know how to get the antiderivatives. This becomes 2w to the 1/2 minus the natural log of w. And I evaluate it at these points. So you plug in 1/4. This becomes 2 times the square root of 1/4, if you want, minus the log of 1/4. And then this is minus what happens when you plug 16 in, so 1/16 in. So it's this. Now, we're out of time and I'm out of slides. It only lets me use 20 slides, but you can easily compute this. This is not terribly difficult to compute this number. So if you take the square root of 1/4, you get 1/2. So you get 2 times a half. And then the other one is 2/4, so that's a half. So what you end up getting, if you do the arithmetic, and I'm out of space, I feel bad, but it's equal to 2, or excuse me, not 2, I just said 1/2. Oh, okay. It's 1/2. Minus, if you use your log properties, this is just minus log 4. So see if you can get that. I'm just using log properties. Does anybody have a question about this? Now we're going to give you a bunch of these to practice. And you guys get to ask questions. Any questions before we go?
Will there be a review for the final?
What's that?
Will there be a review for the final?
Yeah, absolutely. I mean, I'll post some old finals. I'll be willing and able to meet. We can have office hours if you want. We can hold some practice sessions. That's fine. Any other questions? All right, I'm going to stop recording now. Yay.